Okay, so today we'll be studying forced vibrations. In the previous lectures, we had done free vibrations and damped vibrations. Free vibration was when you displace a body with a restoring force, and if you let it go, then it will oscillate freely and for infinite amount of time because there is no damping. And for damped oscillation, there was a damping force present which was proportional to the velocity, and if you release this object, then the amplitude will slowly reduce to zero. That was damped vibration. Now forced vibration is there must be an external force, a periodic force. You can see here that there is a periodic force applied, again e to the power of I omega t, where omega is the period of the force, or the frequency of the force. So the frequency with which the force is being applied is omega. So you are repeatedly applying a force, a periodic force with frequency omega. Say for example there is a swing and you just displace the swing and release it. That will be damped oscillation, because once you release it, you are no longer applying the force, and then there is air resistance, so the swing will slowly come to its equilibrium position. But if you keep on applying a periodic force to the swing, so if you have a swing and you take it to the extreme point and then you release it, and every time it, let's say, comes back, you again apply a force. So you are applying a force periodically. That is an external force is applied with a frequency of omega. So this is a periodic force that is being applied. So let's understand the dynamics of the system where periodic force is being applied. Now according to Newton's laws, mass into acceleration, again acceleration, I'll take it the motion along the x-axis or x direction, so the acceleration is d2x by dt square. Mass into acceleration is equal to the net force acting on the object. So for simple harmonic motion, definitely you need to have a restoring force which is proportional to the displacement, and there is a minus k. Again, if there are damping forces present, then the damping forces is going to be proportional to the velocity, that is dx by dt, and this is the constant. Again a minus sign, because as I mentioned earlier, the damping force is always directed opposite to the velocity. And now in addition to these two forces, the restoring force and the damping force, you have the periodic force as well. So divided by m, you have minus k by m minus gamma by m, and you have f naught by m. You remember k by m was equal to omega naught square, and gamma by m was 2b. You can check the previous lectures. So you take it to the other side of the equation, you have d2x by dt square plus 2b, gamma by m is 2b, dx by dt, and k by m is omega naught square, where omega naught was the natural frequency of oscillation, is equal to f naught by m e to the power of I omega t. So if you remember the damped harmonic oscillator differential equation, there was no external force. This was equal to 0, and we solved this differential equation equal to 0, and that was damped harmonic oscillation. But this time we have a periodic force that is being applied, so we need to solve this differential equation. So the solution, so at steady state, what do I mean by steady state? Steady state means after a certain interval of time, the frequency of oscillation of the swing, let us say, would be equal to the frequency of the applied force. See, the applied force, again e to the power of I something can always be written in terms of cos and sine, so it is a periodic force of frequency omega. So if you keep on applying a force of frequency omega to the system will finally acquire this frequency, angular frequency of the applied force. So if you are applying a force at a certain frequency omega, the system at steady state will acquire the same frequency of the applied force. So let us say, let the solution be of the form x equal to x naught e to the power of I omega t. Again you can see this is a displacement x which is again periodic in nature, and this is the solution of the displacement with a frequency omega. So it has taken the same frequency as that of the force. So if I substitute this value, so substituting this in the above differential equation, if I substitute this value, I still do not know x naught. So my idea or the aim here is to find out x naught. So let us put this, let us assume that this is the solution to this differential equation. So if I put this in the differential equation, if I double differentiate x with respect to t, I'm going to get I omega and I omega out. So I square will become a minus omega square. So here you have a minus omega square x naught e to the power of I omega t, same as x. Again, if you differentiate it once, you would get I omega out. So you have I 2b omega, same as x naught e to the power of I omega t. And here I just put the x as x naught e to the power of I omega t. And on the right hand side, I have f naught by m e to the power of I omega t. So I can cancel e to the power of I omega t everywhere. So what do I have? I have x naught as common. You can see from this equation, x naught is common, and I can take omega naught square minus omega square plus I 2b omega must be equal to f naught by m. So what is x naught? That was our aim. So x naught is f naught by m divided by this quantity. Now please look at this very carefully. This is a complex quantity. This has the imaginary I in the denominator. So let us write it in a more familiar form. So rationalizing it, we get, what do I mean by rationalization? I'll multiply omega naught square minus omega square minus I 2b omega. Here there is plus in the numerator as well as in the denominator. I'll multiply this in the numerator as well as in the denominator. So the numerator is this, I multiply this, and the denominator becomes, this is a plus b, let us say, and I'm multiplying it by a minus b, so it will become a square minus b square. So a square is this, and b square, b is this, I 2b omega. So I square would be a minus, and there is a minus sign, a square minus b square. So you have a minus, I square is minus 1, so minus minus becomes plus 4b square omega square. So this is what you have in the denominator. So you have f naught by m, this quantity, by this. So this is x naught. Now see, this is from your elementary mathematics, high school mathematics. A complex number z can be written as x plus iy, where x is the real part and y is the imaginary part. I can also write it in this form, r into e to the power of I theta, where r is x square plus y square to the power half, or square root of x square plus y square, and what is theta? Tan theta is y by x. This is from your high school mathematics. So same over here, you can see this f naught by m and this quantity is a real number. This can be taken out, but omega naught square minus omega square minus I 2b omega, this forms the real part and the imaginary part. So this is the real part and minus 2b omega is the real part. So if I take x as the real part, omega naught square minus omega square, and y as minus 2b omega. So what is r? R is root over x square plus y square. So square of this plus square of this is this half. This is r, right? So I can write, so you can see I can write this x plus iy in terms of r, this is r, to the power e to the power of I theta. So this is r. So f naught by mc, this is something which is real number, so this I've taken out, and this becomes r. This, if you take the magnitude, this becomes r to the power half and e to the power of I theta. What I've done is I've written this in terms of r and theta, like x and iy in terms of r and e to the power of I theta. So this is x, this is y. If this is x, this is y, then this is r into e to the power of I theta. Now what is theta? Tan theta is definitely, you know, it is y by x. So tan theta is, this is y and this is x. So tan theta is minus 2b omega divided by omega naught square minus omega square. Please understand, there are two omegas over here. Please understand the difference. This omega is the frequency with which the applied force has. This is the frequency of the applied force, the external applied force. You are applying a force with a frequency of omega, and omega naught square or omega naught is the natural frequency of that system. So if it is a swing, then the natural frequency of the swing is omega naught, and omega is the frequency with which you are applying the external periodic force. Omega is the frequency of the externally applied periodic force, and omega naught is the natural frequency of the system or the oscillator. So you can see, coming back to this, you have a half power there and you have this denominator. So if I cancel this, I'll have half over here. You can see half over here and e to the power of I theta, where I know what is the value of theta. Tan theta is given by this. So if this is x naught, then what is x? We know that the solution was x equal to x naught e to the power of I omega t, and x naught is this. So x is same this into e to the power of I omega t. So I omega t plus theta. I omega t, there is an I theta, so I omega t plus theta. This is x. This is x. So you can see that the periodic force had this phase term. E to the power of I something is the phase term. This is the phase term. So what is the phase of the periodic force? It is omega t. The phase of the periodic force is omega t. And what is the phase of the displacement that we get? The phase of the displacement is omega t plus theta. So you can see that the displacement of this oscillator is out of phase by an angle theta from the applied periodic force. Remember, the phase of the periodic force was just omega t, and the phase of the displacement of the system is omega t plus theta. So there is a phase difference of theta between the displacement and the applied periodic force. So in the next class or in the next lecture, we'll be dealing with resonance in systems. Thank you.